Welcome back all. So the next session is on welding automation in nuclear applications by Dr. M. Vasudevan. Dr. M. Vasudevan is a scientific officer H and currently holding position as Head Materials Development and Technology Division, Metallurgy and Materials Group, Indira Gandhi Center for Atomic Research, Kalpakkam. He is a professor at Hombi Baba National Institute, Department of Atomic Energy. His areas of interest, research interest include alloy development, welding, modeling, and simulation, residual stresses, and creep. He has published over 152 research papers in peer-reviewed journals and books, 125 papers in conference proceedings, and holds an international patent. He delivered more than 50 invited lectures at reputed universities and conferences. His H index is 31 and his research papers have already reviewed over 2,500 citations. Dr. M. Vasudevan is holding many additional responsibilities as an editorial board member in the International Journal of Pressure Vessels and Piping and an editor at France IIM. He is an academic council member in Pondicherry Technological University, Puducherry. He is a council member, Indian Institute of Metals, vice chairman in IIM Kalpakkam chapter. Dr. Vasudevan has been awarded and recognized for his worthy and significant research contributions to welding science and technology and metallurgy of nuclear structural materials. He has received several awards, which includes Sharp Tool Awards from PRC Tech, Coimbatore, Stale Gold Medal Award from IIM, IT Mirchandani Award from IIW, DNH Sehron Award from IIW, HT Govindraj Memorial Award from IIW, Young Metallurgist Award from ASM International Chennai Chapter, Group Achievement Award for Excellence in Science, Engineering and Technology from the Department of Atomic Energy, Government of India, Overall Best Paper Award from IIM Kalpakkam Chapter, Indian Nuclear Society Gold Medal from INS, KCP Best Paper Award from IIW, Professor Placid Rodi Cruz Memorial Award from IIW, Overall Best Paper Award from IIM Kalpakkam, National Metallurgist of the Year Award from the Ministry of Steel, Government of India. He also students also receive many awards, Best Paper Awards from IIW and IIM conferences. Sir, I welcome you for the session. Please take over the session, sir.
Thank you. This is my presentation. Okay, mine is not coming yet. You have blocked it or what? Mine is not coming. Hello?
Sir, you just pick your presentation screen, sir.
My presentation, yeah, I'll open it. Yeah, fine. Is it okay now?
Yeah, now it is coming, sir. Put it in slides. Oh, okay, sir.
Thank you for your kind introduction. I'd like to first thank Professor Mugan for giving me this opportunity to join this course of ACT course on robotics and automation. I have been working in this field for quite some time, so I choose to speak on welding automation in nuclear applications. In the nuclear field, welding is the most important fabrication process because most of the components in the nuclear industry is fabricated by welding. You know, in the nuclear reactor, the components are very huge and big. Only few of the Indian industries are capable of making these components, like L&T and some Chandanagar industries, and only few of them we can name them. And so it's very difficult and also a lot of cost involved in fabricating the nuclear reactor components. The components fabricated should strictly follow the codes and standards. Otherwise, you cannot put it into the reactor. So mitigating the defects, any other distortion, minimizing residual stresses, these are the very crucial, important factors when fabricating the nuclear components by welding. And so, by doing all these things, we can enhance the component integrity, its life, and also safety. Also, we can minimize cost of fabrication, and in turn, we can increase the productivity. But whatever you standardize the optimize process parameters, we do mock-ups, and then still we start fabricating, we end up with defects. This is due to the disturbances during welding. So when you do the welding, it's very difficult to control your welding process, and always you end up with some defects or so things. So here, is a critical role. Automating your welding processes can minimize the welding defects, can reduce your post-welding operations, and enhance the weld quality. So based on the degree of automation, we can classify the welding processes as mechanized welding, automatic welding, and robotic welding. What is mechanized welding? Welding in which welding parameters are controlled mechanically or electronically, but only manual intervention is allowed during welding. That is called welding. So from manual welding, moved on to mechanized welding. Then we move on to automatic welding, where welding operations are not interfered. Manual intervention is done only between welding operation, not during welding. That's called automatic welding. Then we have now robotic welding. Here robots are used, they are pre-programmed to different welding paths and fabrication components. That's the latest advancement in automation of welding operations. Coming to mechanized and automated systems, we have a lot of advantages. This increased productivity, consistent weld quality can be achieved, and we can predict the production rates so that we can have other things in place so that cost is minimized, and a lot of variables can be controlled at a time, and we can get the component, good quality component fabricated. However, there are a lot of limitations also. So the automation, automating the welding process, a lot of capital investment is required, and then we need sensing and controlling devices, and we need accurate part location and orientation, and processing planning also required when you go for robotic or automatic welding. So these are the limitations. Even then, we have a lot of advantages. The limitations we can manage with the limitation, and still we can benefit a lot by going for robotic or automatic welding in the nuclear component fabrication. So we will see one by one. This is whatever we have done in our laboratory research. I am going to present most of the results from our laboratory research. Of course, towards the end, I will go talk about some welding application, the nuclear fuel complex also. So we started with the TIG welding system. Around 2001, there was no, we were doing only manual welding. Then we wanted to go for the automated TIG welding system. We approached some industry, the Prime Automation in Chennai. So we got a system which is shown in your screen. 3-axis TIG welding system. You can see a controller on your left side. You can see your controller here. This is your TIG torch, and you can see the servo motors. It is a linear variable carriage, and we have a controller here. So we found we were not happy with this. This is a sort of semi-automatic machine. We started using this machine. Then what we did, one of my colleagues is an electronics engineer. He knows machine programming. So he discarded this controller, entire controller, what you see here. And then he computerized the entire operation, putting arc ignition, arc extinction, and we started controlling in the power source from the PC. And then we came down this computerized welding system that we could carry on a lot of welding. Last 2006, we have been using the system very successfully to develop the ATAL welding technology for heterogeneous welding, TIG welding for stainless steels and grinding steels. I will show you some of the results. Then also we could integrate IR camera. You can see here in real time we could capture the full images and process images, and I will be talking about this in the coming slides. So I am going to show you here the TIG welding technology. I am going to play the video now. Please see the video. Here we apply a thick coating of flux on the joint area. It enhances the process performance by multi-fold. See, in automatic welding, we cannot get more than 3 mm penetration. but by applying a coating of wax to enhance the penetration, single pass we could get 12 of penetration in stainless steels. So we can apply single pass and clean. Since then we have been using this process for welding various thickness components, even plates and see the top side of the back side, back side. See, you can see that some of the plate. This pass in radiographic quality also. So in single pass, we could do large thickness welding. You can see here in the screen cross sections of L304 L7 of the single pass welding. In comparison, right side you can see multi pass. We could do some 11 passes. Whereas here in single pass we could do 8 thick welding. Then bottom one is 12 mm thick 316 L. The right side is multi 13 passes we could do in single pass. The properties are very good. We were very happy and that's why we get it passed on this process. Then internationally, TWA also has developed these process. They have demonstrated double sided 20 mm thick. Same thing we tried here, we could also get 20 mm. We can see here using the same system I told. So because of automation and computerization, we could make a defect-free welds and we could achieve 20 mm double side welding in stainless steels on par with international standards. Coming to new components, this see they were in our center workshop. This X-scan component used as a core sub-assembly. They were welding by manual TIG before we were using this 8 TIG. They were having a lot of problems associated with the resources and distortion. So one X-scan could be welded. This is two valves. They were put together and welded. And you can see the other things inside to support it. But what happened? It took almost 1 week by operator to complete one component. So when you change over to 8 welding, same thing with you can see here with the travel carriage, we could see so many 5 years such a component we could fabricate single day. So productivity advancement we achieved, also quality has improved. We could reduce heat input, so we reduce resources and distortion. We have successfully fabricated these components and we are using in the last 10 years this in our core testing facilities. Then we went on to do pipe welding. You can see here pipe welding. This is again 4 to 5 mm thickness around pipe welding. You can see that we are seam welding, the top side, root side, full penetration. This is the jobs used. We use lathe to rotate the pipe. You can see the pipe welding here. See seam on the pipe welding. Successfully demonstrate our process for plates and pipes successfully, and we tested it in the simulated testing facility on plug-in. So we passed all the after 12,000 hours of exposure, we passed the pressure test and helium leak test. So pipe integrity was very strong with this 80 process, and we are going to use in future our reactor for pipe welding this 80 process. Then next development is this flex storm we are using as a coating. Now we want to develop as an activated flex. This activated deep flex coat where we can use for again pipe welding. You can see here. It is again automated process with wire feeding. Wire feeding mainly used for capping process we are doing to get a good reinforcement. You can see 10 mm thick could be welded successfully. The cross section you can see the bottom. It was successfully welded this also. So heavy welding has been a great success for us in fabricating various components. Moving on to next one, the next component I am going to talk about is fuel subassembly. This is a core component used inside the fuel subassembly. You pack all the fuel pins. You can see rods. You can see here in this case, fuel pins are inside located, and this is the outer one stand. It's made of Roy and another titanium modified magnetic stainless steel, and the area of foot is made of 316 L. So these two, this expand part, center core part and the bottom part, it is boot assembly, have to be welded here. They are using, you can see this welding facility in our center. They are using TIG welding. Now you can see it's again automated process. It is in 2G position, it is being welded. You can see here, welding is done, boot assembly with the X-scan. Now again, we because this require 2 or 3 passes to finish the welding. Like this, so many fuel subassemblies will be loaded to the reactor. Around more than 1,700 numbers is required to start the reactor initially, including fuel, black and reflector subassemblies. So much welding operations are involved in this. So we again suggested ATIC welding. On mock-up samples, we can see mock-up samples we have done. To see the single pass, same thing we could do, and we were successful reducing the heat input and distortion again. And it also passed all the quality. You can see the full penetration achieved in single pass here. You can see single pass, ATIC welding. So ATIC welding technology, whatever you developed in the lab, is now transferred to the industry now. In our central workshop is using for welding various components, pipes like this POPR fuel sub-assemblies, pipe welding various plates, and successfully. But the automation of the process really helped in achieving our requirements. Then moving on to the next one, it's also a variant of TIG welding process. It's called narrow gap welding. This is mainly used for welding larger or higher thickness components. Minimum thickness, minimum thickness we want to do is minimum 25 mm and beyond. And this is supplied. It is a fully automated process. You can see here the machine. You can see here. This is a housed in our central workshop facility. This is a torch. You can see here we have a small camera also here to visualize the welding pass. And you can see here, this is a typical narrow gap weld joint cross section. Down you can see the conventional V-groove joint. Lot of differences. Number of passes required is less. You can see here. So residual distortion are reduced, and the weld metal consumed is less when you shift from conventional V-groove to narrow gap TIG welding. So this we could do for from 40 mm thick to more than 100 mm. Now we are working on 800 mm and diameter component also for AUC applications. Use welding using this narrow gap technology. You can see some of the things we have welded. You can see here, it's a hot wire based, because the wire also heated up. You will be just prior to welding. You can see the pipe 40 mm thick 304L stainless steel pipe. Using a 308 filler wire, 0.0 mm dia filler wire were used. We maintain interface temperature 140 150 degrees centigrade. You can see the root pass done. We have completed the welding. You can see the final pass also here. After completing this pass with the liquid penetrant testing. Then 40 mm thick plate also we could weld. So all the pipes and tubes, I mean all the wall thickness tubes and plates also using it. It's a fully automated process. We were successful in welding various components. Coming to orbital TIG welding, here we are using this process mainly for AUC components like 617M and 304H copper boiler tubes. And we are using pulse current because there are different quadrants. The torches to move through 360 degrees. We are varying the current from quadrant to quadrant. We adjust the current to get the full penetration and defect-free joint. You can see here a welded component. We got a root side uniform penetration. Cross section you can see. The wall thickness was 11.9 mm. Tube body was 52 mm. It required around 11 passes. The fabricated tube qualified radiograph P and liquid penetrant testing. See the cross sections here. Then again we use the same system for ATIC welding of 304L pipes. We are successful in using our orbital TIG welding. Here the torch moves around on the track to weld these. This wall thickness is 6.35 mm. OD is 219 mm. Material is 304 stainless steel. So we could use all this orbital TIG. It's also automated process. We could control everything and we could fabricate successfully defect-free components. Only thing you have to optimize the process parameters, because the sector-wise, after you cross the second or going to third quadrant, the heat build-up, it aids the penetration in the third and fourth quadrant. So you have to reduce the current levels when you go to the third and fourth quadrant to get full penetration to avoid melt through, things like that. So again, successfully use this process for welding of these components. Next one, we have been working on developing technology called intelligent welding. This we require mainly because in the reactor components, when in service, there are failures in the weld, some defects in the weld develop. we want to do carry out repair, because it's once a reactor is in operation, it is radioactivity. Human access is difficult. We have to carry out the repair welding by remote. So we wanted to develop technology. We started working. We have made a lot of progress in this. That I'm going to share some of the results. Intelligent welding is nothing but it's a closed loop feedback control of welding in real time, employing suitable sensors. So we need to sense the torch movement and also control the heat source parameters real time. We need to control the weld temperature so that we get the required depth of penetration and defect free. Weld joint, repair welded component is defect free. So here the main key factor is feedback and decision making to work together. The feedback system and the control algorithm, they have to work together reliably. So without good sensing and precise control, it is not possible. So we have to choose a suitable sensors. We initially tried with the infrared sensing, infrared camera, because it measures the temperature during welding. Is basically a thermal processing method. We thought that should work, but the only problem we faced was the cost and life of the infrared camera. But we could get good results. But now we are moving away from infrared camera to CMOS cameras that are cheap and very small in size, and it can be used in remote locations. First, we'll see some IR camera results. You can see here. You can see here we have integrated the IR camera with the TIG welding system so that in real time it could capture the weldable images. These are the specification of the camera, high band pass filter camera with the wave range 4.9 to 5.1 micron, measurable temperature range 473 to 1773 Kelvin, frame size is 320 to 240, frame rate 25 frames per second. You could see these are the typical thermal images we captured. This is after image processing, the typical well pull image, the temperature isotopes. This we used for using feature extraction techniques, image detection techniques. We could get the features like the length and width of the well pull, and then first derivative from the curve, temperature profile curves to correlate with the depth, grid width, and depth of penetration. Depth of penetration, we use area under the thermal profile, correlate with the depth of penetration. Here you can see, then we developed neural network based models using these as input features, image features, and the parameters, correlate with the depth of penetration. See the extent with the measured weight width and the predicted weight width. See the very good correlation for both depth of penetration, and this is based on neural network model. Then we developed analysis-based models as well to get more accuracy and to achieve that. RMS values of very low value could be achieved for predicting depth of penetration as well as weight. So what intelligent welding strategy we propose to adopt is, you want to use a non-contact sensor. It can be CCD camera, CMOS camera, or combination of DAC camera and IR camera for monitoring well. Then we need to develop knowledge based on signature of edge effects. I will show you some of the signature we captured using IR camera. So temperature field we can measure that can be correlated with weld defects and weight dimensions. And we using DAC camera, we can use stain measurement that can be correlated with the residual stress and distortion or cracks like defects. Then weld surface profile we can capture using this camera that can be correlated with the bit shape and penetration. So first we have to develop a database, knowledge base on the various defects and the weight dimensions correlation with the image profiles. We can see some of the signature image signatures we captured for using IR camera. You can see this entire weld length. We measured the temperature for entire length. We can see that it's almost flat. So then it shows a complete penetration. It's a backside of the. When you get a complete penetration, there is no change in the temperature. It is almost same. Suppose when you measure the surface temperature, if there is a defect like a lack of fusion, you can see here there is a lack of artificially introduced. That is reflected in your signature image. You can see that there is a dip in your temperature curve. This is typical of lack of fusion defects we could capture using IR camera, and this is lack of penetration. You can see here again. You can see the lack of penetration defect. which could manifest as you can see the dip in the temperature curve. Again, this is a tungsten inclusions we introduced in the weld joint that also showed some deviation from the normal temperature surface temperature distribution. We could use this as a signature of various defects for detecting during actual welding. So these are the strategies we would like to adopt during intelligent welding. Here you can see in the GMA welding, some of the things again here you can see temperature is required. See there are some dips in temperature associated with some defects, lack of fusion, lack of penetration, things like that. This is in GMA welding. Again, some defects highlighting the defects during GMA welding. You can see the defects here. It's shown marked in the weld sample. Correspondingly, it's in the temperature curve. You can see here various defects. So these are the things we record. We use surface profile. We can use for calculating the depth of penetration. This can be captured using any vision cameras. So what we want to do using this intelligent welding strategy is, in real time, we want to adopt this for monitoring control of welding process, mainly TIG welding process. This can be extended to laser welding as well for enabling seam tracking to achieve the desired feed width, to achieve the desired depth of penetration, to achieve the desired feed rate, and to mitigate defects in your weld. So this is a strategy we want to adopt for developing remote welding technology for our reactor components, and we are almost there now.
I request participants to mute their mic.
So that we are working on currently. Now we have got a new robo with us to develop this technology that we will be seeing next. You can see here, this is a robo I got. It's a robotic automatic welding system with associated sensors. You can see here. Hello? Hello? Sir, what's the problem? Here we are having a robotic and automatic welding system. We can see here lot of sensors like CMOS camera. It is a laser SIM detector, all integrated system. This including this positioner. It is an integrated 8-axis system. Robo is 6-axis. Positioner is rotating as well as repeatable, so 2-axis. It's all integrated together. So this totally 8-axis system we have got recently in our lab, and you can see here. This is a hot wire fed here. This is a deep torch. CMOS camera is positioned. Laser seam tracker. So we could use these technologies to you can see in a close-up look, CMOS camera and then seam tracker. This is the joint ready for welding. The clamp. This is a positioner table. You can see here welded plates. Using only position, you can see carbon steel plates of this much dimension, 516 to 312 on thick. This is our top side. This is the back side. We passed radiograph. We could successfully weld in because it is automated process and seam tracking everything with that pre-programming everything for programming. We could do it very fast, and we are defect free also, and we could do it at a 2G position as well, 3G position, 4G position. All we could do successfully defect free, not only on carbon steel, we do on stainless steel. You can see here. This is again a 11 thick plate. You can see the top side, root side. You can see the cross section. It required some 9 passes to complete the joint. We could successfully pass radiography again. So we could use the robotic automatic welding system to get a good weld joint, good quality weld joints. Now we are evaluating their mechanical properties, residual stresses, and things like that. System we are finding it very useful. Now with the same system and the robotic welding system we are using for also pipe welding. Pipe welding also can be used, and now I don't have any slide here, so I cannot use. Main purpose is here. We want to use this system to investigate remote monitoring of TIG welding process and just comparing the systems what you have with the what is available at Oak Ridge National Lab USA and Keyword UK. You can see that the leftmost is Oak Ridge National Lab. You can see that they are using this for remote welding, they can see the top one, sorry. Top one, you can see that welding setup. They use some cameras to capture the in this bottom. You can see that weld pull image. The arc is totally not seen. The arc interference is weld appears like a mirror. You can see the reflections because they use the sophisticated cameras to avoid arc interference. See, BWI again can use this. They use laser diode for illumination and CMOS camera. CMOS camera they use for weld pull observation. Again, they could also avoid the arc interference. Which in the arc is totally arc effect is nullified. Whereas in our case, you can see here that the camera we got is only 16 dB, that is 16 dynamic range of brightness. With the arc, still arc effect is seen in the images. You can see during ATAL welding and even multipass, you can see the grooves, multipass welding also. So what is the camera? What we have is a 60 dB is dynamic range of brightness. We need to use 120 dB cameras to nullify the arc effect. Then only arc will be totally not seen. Then we can use precisely the weld pool for image processing and further development of control algorithm to control depth of penetration and bead width. The same technology what we are using now, you are saying, is can be extended to additive manufacturing as well. In additive manufacturing, you need to control the bead width and the bead height. We can use similar cameras to control the bead height and depth of penetration. This can be extended to additive manufacturing process like wire arc additive manufacturing as well. Then coming to these hot facing, see for nuclear reactor component, many of them require, there are friction between components to minimize the wear among the moving components. We use hot face deposits. Also in AUSC applications, you require hot facing deposits. Developing technologies for that. You can see it's a PTAW process in our central workshop. You can see here this machine PTAW process, plasma transfer or machine process. Here overlaying is being done. Here the material here tribology T400 is deposit alloy 617. These are the parameters used. It needs to be preheated by electrical resistance and then also slowly cooled in the furnace. You can see it's a furnace cooling after deposition. You can see the deposited substrate, and this is hot face coating. And we could successfully demonstrate that. This is how the plasma transferred arc processing works. You can see here. This is your tungsten electrode. You can see these inner nozzle and outer nozzle. Outer nozzle we have shielding gas. Inner nozzle we have plasma gas. Also powder is fed through this. You can see here. Through the nozzle, when the arc comes, it gets constricted. That's how it gets a penetrating power arc. The process performance is enhanced. I can see your hot facing deposit here laid on the substrate material. This is the process principle. We could do again for PAPR applications. This driver safety rods use a dashboard piston that require hot facing. The material is modified nichrome steel. We use a nickel-based hot facing alloy. Commercial Deliro 50 for depositing on this modified nichrome. We could successfully develop the technology. You can see here. This is after hot facing. This is a dye penetrant in the past after machining. So we could successfully develop the technology for hot facing of this driver safety rod of PAPR. It is all used in the PAPR now. So this is about PTAW. Again, because of automation, we could do it. So before automation, we work with OnePlus Systems in Chennai to develop this technology. Initially, even sleeves in the grid plate, they helped us because of prime automation. They could automate the process. If they tried with manual things, we used to get a lot of defects. After automation, we could make almost defect-free hot face deposits. So automation really helped in achieving our quality. Coming to next one, because hot facing, so far we are using PTAW process. Now we want to try a low heating process called CMT process. This is a process developed by Fronius. This process, I will see how it, because it's a low heating process, how it works. So you can see this is a mechanism. You can see here what happens during this MIG welding process. You can see there is an arc stuck between the filler wire and the material. The filler wire is, once after the arc is initiated, filler wire is moved to touch the weld pool. So when the wire touches the weld pool, the arc is extinguished and the current is reduced simultaneously. Then wire is made to withdraw. Then that weld pool, the weld droplet detached from the filler wire fall to the material or workpiece to be joined. And then the arc is reinitiated. There is a hot and cold period alternating. It happens very fast. The productivity is not lost, and we could get a low heat input, so we could avoid spatter. And this when we are trying out for hot facing and cladding application. This process now, research is going on. We got the new system in our lab. You can see here, this is a new system, robotic system we got. We have done some deposits. You can see here some deposits, or we are using columnar alloy. You can see here still deposits, hot facing deposit using CMT system. So this we want to adopt in the future. We successfully could deposit. Now we are characterizing all depositor layers. When this is a robotic process, we could control all the parameters, and we are able to get defect-free hot face deposits. And moving on to laser welding. Laser welding, especially we use for laser welding, N-cap welding. See, N-cap welding, this is a fuel element is there inside with that uranium oxide pellets are loaded. Then on the sides of the tube, we need to have plugs that we need to weld. Earlier we were using stick welding. We have now moved on to pulse laser welding. You can see in the lab we developed the technology. This is a laser welding, CNC control laser welding system. You can see the controller, and this is a laser welding system. It's an enclosed one. You can see this is a fuel pin. You can see the typical fuel pin. These are the end plugs here at the top, and this is the center portion. Of course, fuel suppressor we already seen. So in this cross section, you can see here in diagram, this is the end plug material, this is a clad tube. So here we need to do the welding. So we developed successfully. You can see the cross section after welding, and full penetration defect-free we could achieve. These are the parameters need to be controlled during laser welding. This is during TIG welding. Peak power, it's a pulsed laser welding. We could again, you can see the actual welding. You can see this component, the tube being held here in the rotating chuck. This is a laser gun. You can see the inside views shown. So again, we could successfully weld. You can see P91 tubes also you can weld. Clad tube. These are, you can see the joints welded. This is a clad tube. This is end plug. We could successfully weld. You can see here welded clad tubes. This is the waveform of the current. So these are the parameters we used. We could see we measured. You can see penetration is complete, and no process well profile. So we successfully optimized the process parameters for end-plug welding of fuel pins. We did for stainless steel as well as for modified nichrome steel. Then what we did, the same pulse laser welding system, we thought because penetration is limited, it's only 500 watts system. We integrated a TIG torch. We specially designed some fixtures to attach, integrate TIG torch with the laser gun, and we were successful in achieving. So when you couple a TIG torch with the laser welding system, there is a significant improvement depth of penetration to do at higher speed, and and we can again still avoid defects associated with the laser welding process, because we are combining two heat sources here, laser and arc welding sources. Defects like porosity could be avoided, penetration could be uptime, and defect-free joints could be fabricated. Here you can see here, TIG torch position at an angle. It is located, integrated with the laser gun. These are the parameters we used. You can see here, closer look again. This is our 6 mm thick plate, stainless steel plate of 300 mm long. We are doing butt joints, square butt joints. You can see the positions. You can see we successfully welded again using the parameters given down here: pulse power, pulse duration, frequency, current on. we optimize to get a defect-free joint. You can see the cross section. You can see here. You can see the weld cross section, full penetration. This we developed in our laboratory. This technology again. To fabricate joints and then modify them for the mechanical properties, residual stresses, and distortion. We could also run simulation, FEM simulation, of course. That's not scope of my lecture, and we could correlate with the residual stresses. This is in our lab, this system. Then we want to try laser MIG welding. Of course, here again, MIG torch is integrated with laser beam. Of course, we don't have the facility. So we, of course, ARCSI for our welding requirements. My students went and did. You can see here the system available. ARCSI we could weld. You can see top side successfully we could weld using laser MIG welding. These are the parameters. If we control, we can vary the weld attributes, penetration, deposition, and other things. We can control by varying all these parameters. There are many parameters are involved in laser MIG welding. You have to play with parameters to get the desired weld attributes. You can see the cross section again. You can see the triple cap reinforcement on the top and narrow down to the root. And microstructure also get the. Because we are using a filler metal here, we could get the desired frame number. No porosity, no core tracking, nothing is there in 360. So defect-free joints could be fabricated again with the laser MIG welding system. So this is how we are using the advanced welding process, which are also automated. Some are integrated with the robot, like hot wire thick welding, laser welding, laser thick laser MIG for welding of our nuclear structural materials. Successful. Then moving to next one, we are moving on to magnetic pulse welding. This is again good. The process was invented long back. We are trying to use this process for our NCAP welding. The principle involved is explained in this diagram. I mean, in this slide, you can see here there is the current carrying coil. Then here is your workpiece located. Outer one, inner tube, outer tube. So when a current is passed in a short time through the coil, magnetic field is induced in the current carrying coil. There is also eddy current introduced in the outer tube. Then opposing magnetic field is generated. So the two opposing magnetic field between the coil and the outer tube, they repel each other. So it accelerates the outer tube to make an impact on the inner tube. That's how, because the impact velocity is very huge due to plastic deformation, it formed. This exactly we are using for, this tube is a clad tube. This piece is a end plug. We are able to weld successfully using this technology. This is a machine we developed at BRC Mumbai. The entire system is developed, controls everything at Baba Atomic Research in Mumbai. The technology ECAL, they are now selling these machines. This is, you can see the parameters are given, capacity of the systems. You can see the coil arrangement, things like that. Here only coil life is important. That only you should take care. Then here we have done D9 austenitic stainless steel to 360 end plug welding. You can see the welded things. We optimize the process parameters. You can see the bonding and the entry. It's wavy welds, similar to explosive welding because high impact. Due to high impact, the bonding takes by plastic deformation. You can see the wavy interface. There is no melting involved. So we could successfully optimize fabricate. This again, this technology we want to use future welding. And again, ODS cheese, we could also weld using this technology. Nitrom ODS with the 91 ferrite end plugs, we could weld successfully. You can see the bonding cross sections. See here, about 5 mm length, we could get good bonding. So you use copper mainly as a driver to generate that magnetic field, opposing magnetic field, so that impact velocity is huge. And also we have to end plug geometry, we have to suitably design so that the contact angle, other things are important in achieving a good bond. The parameters we use are given in the table: capacitance, voltage, in energy or heat input. You can see time period is the main variable. This is the current to get that. This is the end plug geometry. This need to be optimized to get a good bond. You can see the microstructure. You can see here beautiful wavy structure. Because we did a TEM also, there was no melting involved in the interface. We could get a successful joint. Again, this is again P91 to P91 end plug. You can see the bonding at the interface. Wavy nature of the interface is seen. Here again, D9 fuel pin to 3C end plug. You can see this cross section of the end plug. This is the end plug. This is a clad tube. You can see the wavy interface. So we could successfully optimize the process parameters. The machine is available in BRC. We went and did welding there. Also, I used some systems in Korea for ODS steel welding, and Bangalore also on private companies having this technology, this machine and technology. So these are all about magnetic pulse welding. So we have discussed so far now, starting with conventional TIG welding, moved on to computerized TIG welding, developed TIG welding technology, and then we talked about narrow gap welding applications for nuclear component fabrication. Then we talked about orbital TIG welding. Then we moved on to intelligent welding. Then we discussed hot wire TIG welding, and then we then further moved on to laser welding, hybrid laser welding, hybrid MIG welding, hybrid laser TIG, laser MIG, then magnetic pulse welding. This is all about whatever I presented about, whatever research going on in our laboratory, materials joining laboratory at Kalpakkam. Then I want to speak on some other things going on, nuclear fuel complex in Hyderabad. They are making fuels and then fuel bundles for PHWR. This is the already we have established technology. They fabricate fuel bundles. They use here again. They use UO2 pellets encapsulated in a thing called cycloid tubes. They use cycloid clad tubes, and then they are welded with end caps using resistance welding process. You can see here fabricated fuel bundles. Here you can see here 19 element fuel bundles are used in the 200 megawatt, 220 megawatt electric. Now 500 and 700 we are using 37 fuel element bundles. You can see in the right side. So NFC is in-house. They developed all the technologies and they designed the machines, and with vendors they developed the machines using successfully. You can see this. This is your end plate. This is end plate to hold the fuel pins together. It is welded by robotic resistance welding. We will be seeing later. This is your clad tube, zirconium cycloid clad tube. You can see the end plugs, and then you can see the UO2 pellets here. They are loaded inside. Then end plugs are welded. Here are some appendages here on the each pin. No, you can see some appendages are there. This mainly gives space between fuel pins because the coolant has to flow through the fuel pins, extract the heat from the fuel pins due to heat generated due to fission, and then water. Here they use heavy water, no, and that heated up, and then that heavy water in the second it heats the water for producing steam. That's how this plant works. Plant works. You can see here these are the projection resistance welding using electric gas shielding for welding appendages, spacer pads, bearing pads on empty fuel tubes on the outside. This is well established for PHWs. This is customized and then extensively used day to day. It is being used. These machines are designed and developed by Nuclear Fuel Complex Hyderabad. Again, coming to end plug welding, again the resistance offset welding process is used. Again, you have to control the current, time, and the force involved to get the quality. And because this is the primary containing the fuel pins are holding the fuel. So the fuel pin failure is not at all accepted in the reactor because there should not be any radiative leakage from fuel pins. Any fuel pin failure is there, immediately we have to stop it and see what is happening and then work or fix that. This is the first barrier to release of radioactive material. So the fuel pin quality, weld quality should be very good. So they have successfully established all the technology. We are generating power in PHWs successfully over the years in India. Last one is using robot that end plate welding. The fuel pins are held together. Here you can see that. Then to end edges, you can see both ends we are using a circular disc sort of thing that is welded here using a robot. And resistance welding process is used. Projection type resistance welding. And you can see this. These are all moving, automated. Everything is automated. So every day they are making so many fuel bundles for our reactor, power reactor requirements. This is being done in NFC, Hyderabad. Then coming to the latest advancements, what's happening in reactor vessel fabrication? If you see, a lot of advancements are happening in foreign countries. We also want to adopt. See, this is called a narrow depth multi-pass laser welding. You can see here, they make the suitable. It's a 50 mm thick here, 20 mm joint, 3 L joint, 50 mm. You can see the groove preparation, other things used here. Use a suitable laser gun and flare wire also. Flare wire rate is controlled optimally to get a defect. You can see the cross section. With the minimum number of passes, they could weld using this kind of groove. Here you can see 20 mm thick could be welded. This is the root side and then top side. Again, cross section showing. By multi-pass laser welding, they could demonstrate. This is a futuristic process. It's being considered for welding reactor pressure vessels, and reactor vessels, which has a thickness of 30 mm in so large thickness welding can be carried out using multi-pass laser welding. It has been demonstrated internationally, but we want to adopt in future this kind of process. Then pipe welding now, friction stir welding. You can see US, they have demonstrated successfully in this process for carbon steel pipe welding. I'm going to play the video so that you can appreciate how this works. This is also a fully automated system. This is 6 mm thick pipe. They have successfully demonstrated using friction stir welding process. This is done in US. Of course, we also want to do in future for stainless steel pipe welding. You can see the video live. Say they use a tracks for the uh, movement of this tool, friction stir welding tool. You can see here, this is a track. You can see this is the welding being carried out in orbital welding fashion. It's orbital friction stir welding. It's for pipe welding mainly, even cross-country pipelines. The requirement is the tool welding. You can see the tool weld into steel pipes. See here, it's moving on the track. See here, generator. So to avoid the hole at the end, they are doing something. You can see that they use the extra piece to stop the process so that the hole in the end is avoided. You can see here it is fixing the extra piece at the end. So welding will be completed at the extra piece, not in the pipe. And so the hole at the end is avoided. And he has fixed the extra piece. You can see that extra piece. I'm playing the video again. Inside and all they use support something at the welding joint area. So he is keeping the extra piece of material, finish the process so that no hole is found at the end of friction welding. Fine. In a reactor, we have stainless steel pipes for very longer lengths, and a lot of welding is involved. In future, we adopt this process. As of now, we are using this orbital TIG welding process, but we may move on to this in the future so that still longer life would be achieved. Stainless steel pipe. And see, the welding is over now. We will remove that extra piece, then joint is complete. This extra piece, you can see the hole on the extra piece. We will cut and remove it. Yeah, nicely done. Job is done nicely. And that's it. Pipe welding is over. It's a solid state welding and without filler metal, fully automated process. You can see can be used for welding on cross-country pipe lines. So coming to the summary, welding automation uses robots to increase the performance of production of welds. This automated welding will increase the speed, precision, quality, and also minimize the chances of errors or weld defects compared to manual welding. The robots are very precise, move smoothly at considerable speed by a pre-programmed path. Being computer-based, they can be programmed, have sensors and control algorithms to follow the scene and also apply the corrections in real time to produce defect-free joints. High quality precision welding is guaranteed, and defect-free welded components are manufactured in large quantities through robotic and automated welding. With that, I finish my lecture. Thank you very much for listening. Any questions you can have, ask now. I'm ready to answer. Any questions, please?
So any questions, sir? Sir, Vasudevan sir, we have some questions in the chat box, sir.
Yeah, about electromagnetic, I am an electrical engineer. There will be huge current. So, what type of core material do you think that they use copper-based coils only? Copper-based coils, but the coil life is important actually, because often coil failures are happening. So that is what that's a major issue with the system. Have I answered the question?
Yes, sir.
Thank you.
Sir, one more question is there, sir.
Which will be wound on what type of core? These things only the people involved in that developing the system. I am not directly involved. Maybe they only can answer your question. I don't know what is that they do.
Okay. Okay, if there is no question, we thank Dr. Vasudevan for his wonderful lecture.
Yeah. Thank you very much.
Thank you very much.
So I will
Thanks.
send the questions. Yeah.
Yes. Okay, sir.
Thank you very much.
Sir.
So I
Thank
will
you.
close it.
Yes, sir. Yes, sir. Thank you so much, sir.
Thank you. Thank you.